Hello everyone. So welcome back after the last week's holiday. So we will discuss about the midterm date and also we may have to do a couple of makeup classes for the sort of some last days. Okay, so we will discuss that one more people come in. So any questions before I go forward? Okay, there are no questions. I think I can go forward. Okay, so let us do a really quick recap of the basic techniques we have learned. Okay. So sticking to continuous time population models, we can write model like this. The rate of change of population size is a function of population size, some function of population size. So this is basically the entire population growth rate. Okay, and typically this can be written as n times r times n. Okay, so r basically now becomes the per capita growth rate. So I think by now we would know that n dot corresponds to population growth rate. And n dot by n corresponds to per capita rate. Okay. And then when we want to write down a mathematical model, we sort of argue out from first principle, what are the functional forms for F and R? Sometimes it might be easier to write F directly, the entire population growth rate. Sometimes it might be easier to write down the per capita population growth rate. Okay, so keep that distinction in mind. And once we have, how do we go about sort of making predictions or analysis of this mathematical model? We look for what we call equilibrium. Equilibrium or population sizes at which the growth rate is basically zero. Okay, and how do we basically find this? By solving f of n star is equal to 0. So but equilibrium can come in basically two broad categories. One could be stable or unstable. So to know if it is stable, we need to calculate the derivative of f at n star. If this is less than 0, this means we have as n star is stable. If this derivative is greater than 0, we have an unstable equilibrium. And remember that this is a measure of local stability. What happens if we make small perturbations? Okay. So with that, now let us stop where we let us go back to where we were last time. We were discussing how do we incorporate harvesting in simple population models. So we had dn by dt, and we said that in the absence of any harvesting, we have a logistical population growth, and there are some additional deaths because of harvesting. Okay, now so how do we write down h? And we did a very nice lab assignment on this, and there were many forms of h that you all came up with. Okay, in terms of graphs, we consider two possibilities. H of n is constant, and we argued why this is a very sort of unrealistic scenario. Okay, and then a second possibility was basically a constant times n. as the population of, if you think of n as prey now, as the population of prey increases, the harvesting increases proportionately. Okay, and then we also come up with, but this this sort of misses out a few biological scenario. For example, if there are finite number of predators, they can't keep on consuming just because the number of prey are more, right? The per capita consumption is a constant. The entire predator population might satiate. So we also thought of a more saturating function, basically a function that looks like this. Saturates to some value. Okay, now there are many ways of writing this kind of a function. Let me write down some standard forms of doing this. Okay, so this is let's call this 1. Okay, let's call this 0. Let's call this 1. Let's call this 2. So if you were to plot this, you will find, so basically, how do we plot this? So just n is equal to 0 will give rise to a 0 harvesting rate, right? And then when n is very, very large, so this 1 becomes irrelevant. So you have an divided by ahn, therefore it basically becomes 1 over h. Okay, so I think I should do slightly different notation. Let's call this cn. Okay, cn here. Okay, so I think what was the notation we used last time? But then I don't have the note. Should we use hn here? H times n? Then I can stick to that. I think this was hn.
Yes, sir. Okay,
so let's stick to this hn here. Okay, and then we have a form of this type. Okay, so so there are some interpretations that are possible for AC terms A and C here. So that we will discuss later. But so broadly, sort of mathematically, this is how it looks like. So in fact, what I prefer is slightly different notation. We can still keep the H here the way it is. Okay, let's write this in a slightly different way. Let's write them in the same units on the denominator. N0 plus N. Okay. Now, what's nice about this kind of a notation is that what's the maximum value the harvester can take now? It can take a maximum value when n goes to infinity, and that will be basically h. The maximum value that this function can take is h. And let's say when n is equal to n0, let's look at n is equal to n0. What will be the value of the total harvesting rate? So n0 divided by n0 plus n0, that will be h divided by 2. Okay. So therefore, n0 is also called half saturation constant. So it's the size of population at which the harvesting rate is half maximum. Okay. Of course, there are other ways of writing this function. So we will discuss those later. And again, if you're interested in the saturating functional forms, there is a very general form one can write, which is h n power theta divided by n0 power theta plus n power theta. And I encourage you to sort of play this functional form for different values of theta and see how it looks. Okay. A small exercise to plot h of n for different values of theta. And when theta is equal to 2, we also call them sigma function. Okay. Okay, so there are many different forms of this, harvesting rate that can happen. So this is also called So many of these forms were first sort of, written down by a famous ecologist named Holling. So this is called Holling's type 1. This is called Holling's type 2. It was in 1960s or so. Holling's type 3. And they're all called basically functional forms. So basically when a predator consumes prey, okay, so what is the rate at which predators consume prey, and that consumption functional forms can be of these sort of broad categories: constant, linear, saturating, but a hyperbolic function, and then a sigmoidal like functions. Okay, so they are all called functional forms. Okay, so what we have already analyzed model 1 in the last class. So today we will do model 2. Okay, so let's look at the, this is all Holling's type 2 functional form. Let's write down the equation now fully. dn by dt Rn 1 minus n over k minus h n divided by n0 plus n. Is that right? So now what I'm going to do is I'm going to write everything with 0 right now. You will know why I'm doing this very soon. Let me write down everything with 0. Okay, is that fine? So remember the 3 steps that we need to take when we're analyzing mathematical models. The first is rescaling parameters. Second one will be finding equilibrium. Third one are stability analysis. Is that right? And then plot bifurcation diagram. So let's start with 1, rescaling now. So how many parameters does this have? 1, 2, 3, 4 parameters, which is substantially more than what we have been dealing until now, right? There are 4 parameters. In a simple logistic model, I could get rid of one of them easily and convert them to only 2 parameters. So we have now 4 parameters. Okay. So let's see how we can simplify this. Okay. So this is a sort of, where will you start? Remember the logistic model, what did we do? We took n by k0 as a new variable, right? Can we do the same approach now? We can. Okay. But is there an alternative? Is there an alternative approach?
How can we apply that? I mean, we won't be able to uniformly rescale n all the n's in that equation that way, right?
Exactly, you're right. So that's we can do that, but does it get rid of all other n factors? No, because when you look at this, there is n0 plus n here. There's another. So basically, there are 2 parameters in this model, right? That represent population sizes, right? K0 and N0. Can we get rid of both of them? Is it possible to get rid of both of them? No. So when you have 2 scales that are intrinsic to the system, how many can you get rid of them? You can measure the second one as a ratio of the other, but you still need one of them, right? Okay, so you cannot get rid of both of them. I can only get rid of one of them. Okay, so now how many rates are there? So these are the 2 parameters corresponding to population sizes. What about the rates? What are the 2 rates here? So those will be R0 and H0. Is that right? There are 2 sorts of rate functions, rate parameters. Okay, and again, we can only get rid of one of them. We can't get rid of both of them. Does it make sense? Okay, so we now have to, and of course, yeah, by the way, R0 and H0 don't have the same dimension. Keep that in mind. Okay, so but so there are 4 parameters, but we can divide them into broadly 2 categories. Okay, and we can eliminate we can sort of guess right away that we can probably get rid of 2 parameters and reduce this model to from a 4 parameter model to 2 parameter model. Is that fine? Okay, so now let's start doing this. Okay, so let me choose to eliminate this. So
Sir,
whichever, yeah, go ahead, Akash.
can you explain one more time why we cannot get rid of 2 rate parameters or 2 population dependent
So
parameters?
think about the following, right? So let's say um, uh, we want to measure heights of boys and girls. Okay. So let's say there is an average height of boys, which is let's say 5 feet, and then there's the average height of girls, 6 feet. Okay. And now these are the 2 parameters now, right? Let's say there are other factors that depend on these 2 parameters now. Is it possible to sort of, so we can do one thing, we can write, girls height, as a ratio of boys height, or the other way around. Is it possible to get rid of both of them?
No.
Right? So when you have 2
Yeah, okay.
parameters, we can only eliminate one of them, right? So
Okay.
basically, what does it mean to eliminate? If you think about it in a very fundamental way, it is basically choosing your fundamental unit of measurement. Okay.
Okay.
For example, when we say in physics 1 meter, right? 1 meter was whatever that length is called 1 meter is an arbitrary choice, right? Okay. So for example, in SI units, we have 1 unit of charge, which is not same as the 1 unit of charge in CGS units. So when we have multiple quantities that depend on, have their own scales, we can measure everything in one scale. So usually we can always eliminate the number of parameters by 1 of the same, of having the same units. Now imagine if there were 3 units for population sizes. How can we eliminate? How many can we eliminate? We can usually eliminate only one of them and reduce it to 2. We can't make it more than 2 unless they are the function, somehow the mathematical forms are a bit simpler. Okay, that's the basic idea.
Okay, thanks.
Okay, now so let's try to eliminate N0 first. Okay, which is an arbitrary charge. You could have done exactly the same for K0. It's entirely your choice. It doesn't make a huge difference. So now to do that, what should I do? And let's now define a new quantity, y, which is equal to n divided by n0. Okay. So when I do this, what does that mean? I now need to basically, what I can do is basically I can replace n by n0 times y everywhere. Shall we do that now? If we do this, what do we get? So we have on the left hand side, we have n0 times dy by dt is equal to r0 n0y 1 minus n0y by k0 minus h0 n0y n0 plus n0y. Is that right? Okay, you can see some cancellations can be done now, which is you can cancel this. Okay, so second term basically now becomes h0 y divided by 1 plus 1. But what about the first term? See, this hanging around of n0 on the left hand side is not very pleasant. Let's divide the entire equation by n0 now. Okay, so what do we get? So we get dy by dt is equal to, this n0 goes 1 minus y divided by is that fine? This is what we have now. A simplified equation. Okay, so let me go to the next page now. So what else can we do now? Can we do a few things before we go? Okay, so let's do one more thing. Okay, so I told you the next thing we have are 2 rates. How do I eliminate one of them? Basically, again, divide, right? So let's divide the entire equation by R0. Is that fine? Let's divide the entire equation by R0. You could have also done the opposite way, which is divide the entire equation by H0. There is a reason I'm not doing it. The reason is that I want to know how the equilibrium and stability changes as a function of harvesting rate. H0 is a measure of harvesting rate, right? So therefore, I want to know how things change as a function of H0. So I don't want to eliminate H from my system. So, but instead, R0 is something intrinsic to the population anyway. That's not something that's going to be changing. Okay, so it's okay to eliminate R0. Okay, let's divide the entire equation by R0 and go to the next page. So what do we now get? We get D. Yeah.
Small question with respect to like H, you're not dividing by H0 for another reason that H0 could take the value 0, right?
Yes, that's also absolutely true. Yeah. So yeah, that's also very valid way of saying it. Yes, the moment I divide by 0, the no harvesting is ruled out, right? That's not a desirable situation for us. Okay, great. That's a good point. Okay. Is that right? I hope I'm not making any mistakes now. H0 divided by R0 times N y by 1 plus 1. Is that fine? Okay, now let's relabel a few things. Okay, this entire thing is a big thing. Let's just call this H. Okay, H0 divided by R0 H0. So what's basically what I told you that R0 and H0 don't exactly have the same units. In fact, R0 times N0 has the same unit of H0. Okay, so now we have a new parameter H. So in some sense, what we're now doing is we're measuring the harvesting rate in terms of the intrinsic birth rate of the population. Okay, so we are calling that H. Okay, so H is equal to H0 R0 by N0. Let's now make another. So we're measuring the carrying capacity in units of N0 now, because we have anyway changed our entire measurement of population densities to in terms of N0, right? Which is the half saturation constant for harvesting rate. So we're going to measure, continue that. Is that enough? Are we done, or do we have anything else hanging out somewhere?
The time term.
The time term. So now this side will look now pretty clean, huh? Let's write down this side. Minus H. What about the left-hand side? See, there's an R0 here. So what we can do is the following. We can do the following. We can define a new time scale this way. Okay. So there basically now we have dy by dt prime. Meaning we are basically changing the time scale over which we are looking at the entire phenomenon.
Here, instead of changing time scale and doing this division, wouldn't it be better if we had initially divided by k, like how we did for the logistical equation? We divided by the coefficient of the y in 1 minus 1.
Why don't you try that out and see if you can still avoid this time rescaling?
Yeah, it does, because we get the coefficient of the logistical part as R0 by, we just get R0 over that. And the other coefficient becomes H0 by K0.
Other coefficient becomes, but you still have R0 and H0 both, right?
Oh, okay. Yeah.
To eliminate R0 is the only way. Okay. So this is our simplified equation which now has two parameters. And in doing so, we haven't lost any information. But let's just remember, N0 cannot be 0, R0 cannot be 0, and both of them are reasonable, right? Okay. And with that, as long as that's like, R0, 0 anyway means that, there is no population to sort of begin with at all. There will never be a sustainable population. So it's kind of meaningless scenario to consider. So this is the sort of new model we have. So any questions on rescaling part? Okay. So
I have a question. I still
Yeah.
don't understand what H and K represent.
say it again, sorry.
I still don't understand what H and K represent, like H0 by R0 and 0, and we rescale that and call that H. So what does H represent?
So we know what H0 represents, right? H0 is the max. So if you go back to the first
Maximum
equation,
harvesting rate, yeah.
it's the maximum harvesting rate, right? Okay, let's look at here. This is the maximum harvesting rate. So you're dividing the maximum harvesting rate by the intrinsic growth rate of the population. R0 is the sort of intrinsic growth rate of the population at low densities, right? Okay, so you're dividing it by that. Okay, that means you're but remember that R0 has the dimension of still has a dimension of n. Okay, so so H0, okay, this is small. So one thing to keep in mind is that H0 is the harvesting rate of the entire population, right? Maximum harvesting rate of the entire population. R0 is the per capita growth rate, is that right? R is actually the per capita growth rate, right? Whereas H is for the entire population. So how do you convert now R0 to the population level growth rate by multiplying it by a number, which is population size, that happens to be N0 here. So therefore we're comparing, when we are, so the idea of, coming up with new sort of, parameters, whenever you come with new parameters, think of their meanings. Usually they always happen to be ratios of similar quantities.
Right.
Okay. It's not necessarily true all the time, but usually they are. They often happen to be dimensionless. So when you do rescaling, the new parameters often are dimensionless, meaning they were ratios of similar quantities. Okay, and that's all. That seems to be the case even here. Okay, so K is dimensionless, so is H is dimensionless now. Okay, and so is Y, because Y is divided by N, right? Remember Y itself was equal to N by N0. Okay. Okay, so we have this model. Now let's try to analyze this model. Okay, so let me add a new page. Okay, now how do we go about this? So always, do it graphically because it provides you a good intuition. Okay, one is, of course, you can sort of blindly go and sort of, find the roots of this equation, right? Go back, let's say if I go back to page 1, apply this and find all the roots mathematically. Okay, and then apply this mathematically and find the stability and so on. I will not be doing that. I'm going to just show you how graphically we can arrive at many of the results. Of course, we will need some mathematics here and there, but we'll minimize the usage of unnecessary algebra. Okay, so with that, let's start doing this. Okay, so let's plot. There are two functions, logistic function, right? And then that is subtracted by a harvesting function. Exactly like the last time, we can plot both of them on the same graph, logistic function. This is K, right? And then we can plot the harvesting function. How does the harvesting function look like? Harvesting function is H y times what happens when y equal to 0? When y is equal to 0, then harvesting is 0, and when y is maximum, we will reach a maximum value of H. So here is the thing: we don't know what is the maximum value of H, right? So maximum value of H can be a very small number, which is less than the maximum value of this one. It can also be a large number, which is much more than the maximum value of this. Is that fine? Okay, so let's consider both the possibilities. So for small values of H, this is how it will look like. Do you agree? No, H small. Is that right? Okay. So in the previous case, we had a straight line that was the harvesting function. Now we have a saturating function. And wherever they intersect, we have an equilibrium. This is one equilibrium. This is the other equilibrium. Which is stable, which is unstable now? Look at the zero equilibrium. Zero equilibrium. Nearby, what is more? Logistic growth is more than the harvesting growth, which means any perturbation you make, the logistic growth will overtake the harvesting. Okay, the initial growth rate of the population is higher than the harvesting. Therefore, this is an unstable equilibrium. Okay, unstable I'm plotting by red here. And what about this? When I'm here, if I'm at a slightly larger value than this, the harvesting is more than the growth. Therefore, it reduces, right? And on the other hand, if I'm on the lower side, the growth is more than the harvesting. So this basically is a stable equilibrium. And sort of it makes intuitive sense, right? Because when you have small amount of harvesting, the population carrying capacity has some value k, and you are just below that carrying capacity now. Okay, so that's where we are with the small harvesting rates. Okay, now what happens? Now let us say we want to consider very large values of h. Okay, that's other extreme. And how will this function look like now? This will increase like this and go like this. Is that fine? Very large values of x. So if you do that, what are the points of intersection? How many points of intersections are there?
One.
Only one point of intersection, which is here, right? And is it a stable equilibrium or unstable equilibrium now? So now the thing is, I have only one point. It's going to be difficult for me to write in two ways. So I'm going to, please excuse me, I'm going to write another 0 here again to represent the same equilibrium. Okay, just writing here. Okay, but this is still 0. So we have only one equilibrium. Is it stable or unstable? Again, make perturbation to the right side because the left side perturbation has no meaning. Okay, and if you do that, the harvesting is more than the logistic growth rate. That means at even at very small population densities, the harvesters just take away whatever they find. So what will that cause? It will basically cause extinction. So this now therefore becomes stable. Implies only y star, some y, let's call it, y that is less than k is stable. Is that fine? So we have two, in this case we have two, in this case we have only one. Have we covered all possibilities? Is there something in between? Okay, so now that's not very evident unless you plot much more carefully, not like the way I am plotting. Okay, so let's just do it again. So let's see what happens. This is only two possibilities, and if that is the case, we will get exactly same results as previously. Okay, okay. So it really depends on some factors. It's not very evident what happens, but let me know if the following is actually a possibility. So we have this. Okay, let me know if this is possible. I'm writing the harvesting function now. Oh, sorry. Do you think this is a very, very badly drawn graph? But I hope you're seeing what I'm. Let me just write this again. This is so badly written. Think of it as a zoomed in version of that. So you have H is actually large, not too small, but it does this. Is this possible?
Yeah, if you choose a value of H intermediate.
So for some intermediate value, this actually is possible. Okay. And how many equilibrium do we have now? We have one equilibrium at 0 as before, one equilibrium less than K. We have another equilibrium here. Okay. So let us look at stability of all of them. Okay. So let's look at the stability of, 0 first. What happens? Let's say if I now make a perturbation from 0, small perturbation, the harvesting is more than logistic growth, right? Which means there's a net negative growth rate. So what happens in that case? We will have populations will quickly die off. Do you agree? A small perturbation, it means harvesting is pretty high, so therefore the population just dies off. So therefore 0 is now a stable equilibrium. This is similar to the H large case. Okay. However, let's look at this large population size here. Again, make a small perturbation. What happens now? For a small perturbation, the population, the harvesting again is more than the logistic growth. Again, this will lead to decay of the perturbation. On the other hand, if I make a perturbation to the left side, which means I remove a few individuals from this equilibrium, the logistic growth is more than the harvesting, right, in this regime. So therefore, this is also stable. I'm plotting stable with solid blue circles. What about the intermediate? Can this also be stable? So let's look at what happens here again. This is the equilibrium. I made a small perturbation. So the logistic growth here is more than the harvesting. So what would it mean? A perturbation made to the right has a positive growth rate. So therefore, the perturbation will just grow. On the other hand, if I made a perturbation to the left side of this, the harvesting is more than the logistic growth, which means there's a negative growth rate here. Therefore, the population decays. So therefore, from this equilibrium, if I make perturbation in either of the directions, what happens? The population goes away. The perturbations grows. Therefore, this is an unstable equilibrium. And these two are stable. Do all of you agree with this? Any questions on this? Okay, just think of the implications. What are the implications of this? Before we sort of, do more mathematics of this, what are the implications if this is true? Any thoughts?
I think the unstable form is that the threshold beyond which the population beyond which populations grow towards the other stable equilibrium, whereas below that they go to extinction.
Okay.
Harvesting regime.
Okay. So what is the implication, biological implication of this?
So the population goes lower than that, then it crashes to extinction.
Okay. Okay.
Whereas after the unstable point, it grows up to.
Yeah. Can you sort of phrase it in a slightly
Sustainable.
nicer way?
You could say that it's sustainable after.
Yeah, you're almost there. Can anybody help?
Threshold. There's a
it-
threshold above which, if you H increases, then you get a stable. But if it's
No,
below a
but this is
threshold,
for a given H. See, I'm not changing H here, right? X-axis
Okay.
is population density.
Okay.
You know, H is fixed.
So then if the population size is above for a given intermediate H value, if the population size is above a threshold, then it will be in stable equilibrium. If it's below a threshold, it will go into unstable. At a particular time, it will go to unstable.
Yeah, you are stating what's there in the graph, but I want you to say something more than that.
Something like for a given harvesting rate, you can get at the number of harvesters that you will require for a, yeah. So if you know there are sorry, I kind of confused myself. Sorry.
I mean, sort of, you have said, literally what is there in the graph, but I wanted to just add a couple of more additional small points.
So the equilibria are locally stable. If there's a
Okay.
large enough perturbation, it will move to the other equilibria.
Okay, that's a good point. So what's the ecological implication of that? So large perturbations take you far away, right? So what is the implication of this ecologically?
Where we start, the initial condition will decide where it will reach. Like if I start.
So initial condition determines the outcome, right? So all else, so initial condition, or basically initial population size in our case, right? If I determines final population size, which means that if I imagine there are two two lakes, with exactly same levels of harvesting patterns, right? If one lake had small initial population of fish, that will be in the extinct state because any new introductions will be quickly harvested out. The exactly similar lake elsewhere, if it had a high initial density of fish, despite the fact that it also has the exact same harvesting properties, can sustain large number of fish. Is that right? So these are also called multiple stable states. Under same ecological conditions, you can have multiple stable states, which is sort of very counterintuitive if you were to think in a very deterministic sense, right? Or rather in terms of the uniqueness, if all else being equal, I will always get this outcome, right? That's not necessarily true here. One small change, which is the historical properties determine the current state. Another way of saying too is historical contingencies matter. Okay, what else? Then another very sort of go ahead.
So yeah, it also shows that for a fairly simple sort of system where we only have one predator and one prey, it can have multiple stable states. So I was wondering if there is any way to predict as you add more and more interacting organisms, can you predict the number of stable states that an ecosystem can take?
Yeah, that's a good point. So it's possible to do what you are saying. It just requires much more complex mathematical sort of analysis. But yeah, it's entirely possible to sort of do that kind of an analysis. Okay, so think of another simple scenario here. Imagine there is a population currently at this level. Okay, there is harvesting and there is it is in this equilibrium. For some reason, in that, let's say in that in some specific time scale, the harvesting suddenly was very high, or maybe let's say there was forget about the harvesting now. Let's say this was the current harvesting rates in a stable state. Imagine there was a catastrophic event, climatic event that reduced the population to here, that killed a whole bunch of population. It has crossed this unstable equilibrium now. This is where you are landed now. What happens to this now? It will actually now become extinct, right? Okay, so because the perturbation has crossed that unstable equilibrium, if it was even here, it was totally fine. It has sort of come back, but beyond this point, it will move towards extinction. Okay, so this is another possible scenario that can happen. Of course, this catastrophic event can also be entirely harvesting itself. If there was one bout of very heavy harvesting, it won't recover anymore because it's only a locally stable state. Isn't that right? So, okay, to have the implication, let's now analyze this a bit more. So before I analyze, there were a couple of, it's now 11:50 and some people may leave very soon. So I wanted to check two things. One, people were asking about the midterm exam. So maybe I was thinking sometime next Friday, would that be okay? Friday, or actually, can you come on Saturday for 1 hour? Next Saturday? Maybe I can also just do a poll and check what time works for everyone. Is that fine? Because the exam requires everybody who's crediting. So I will just do a poll. That might be easier in case somebody is absent today. I don't want them to be. So maybe they say next Friday or Saturday is my current plan. Okay. So class hours might be.
You mean next week, right? Or
yeah. Yeah, I think next week makes sense. Yes. Next week, as in 14th, 16th. Let us say April 16th. And it would be 1.5 months from the end of the semester. I think that's a good time to just check. It will be very short, maybe 1 hour maximum. Okay. Midterm exam. Is that fine? Okay. Yep. And the second point I wanted to discuss was, so there was this suggestion from the academic registrar or deans, if I remember correctly, that the total in-class assignment is sort of out of the exam. Assessment is recommended to be 70% and exams must be 30%. It was a recommended sort of thing. So I was thinking that maybe then we can, so now I think the current distribution I have given, I have set 60 for the in-class plus homework, right? And then some 10 for the midterm and 30 for the final exam, right? So maybe I will make the end term plus midterm is equal to 30%. Okay. And we will increase the assignment and homework and the assignment part together to 70%. Okay. So that's a small modification. Okay. That I will also announce via the Canvas website. And the third point I wanted to mention was, since we have missed a few classes, I wanted to have a makeup class. Would Saturday afternoon work for everyone? I may need 2 such slots over the next month.
That is Saturday the 10th.
Sorry?
Saturday the 10th.
Saturday, sorry?
Saturday the 10th of April. 10th. As in
10 o'clock in the morning. Yeah, Saturday 10th. So this coming Saturday would be one day I want to take, and then maybe another one after 2 weeks. Maybe I think see, if you remember, we have 1 hour of less class per week because of the timetable conflicts we had, and then we also have, I think there have been a few holiday. Last Friday was a holiday. Next Wednesday will be a holiday again. And then there will be one more break during the PhD interviews time. Okay. And I also missed 2 classes in the first week. So there have been 4 to 5 loss of classes, and also there's every week, less number of hours. So I wanted to make up for those because we're also going a bit slow than I have anticipated. Okay. So, so Saturday afternoon will be ideal for me. It's a 2 to 4-ish. I will send an email to make sure. Okay, tentatively we can keep it Saturday in the afternoon. Okay. I mean, UG students are the ones who will have a biggest problem with this. So I want them to speak up if they have a problem.
So which Saturday is this? Like
The coming Saturday? Yeah. That's the immediate one. Yes.
Okay, I think we might have an extra class, but I think that's being scheduled for the morning currently. In case it's being postponed, I'll let you know.
So I will send a, let's finalize by today, if possible, because I also can,
So could
sort
we
of,
have it by 3:30 or something? I
Ah.
think I have an extra class from 2 to 3:30. That's why.
Coming Saturday?
Yes, sir. Coming Saturday and the 17th. That's why.
Or both the Saturdays? Okay. So, we will figure out,
Yes, sir,
so somebody, so then how about morning, let's say 12 to 1:30 or, 11:30 to 1? Would that work? I prefer one fixed slot that we can use for, a few weeks.
The UG biomajors have a quiz actually in the morning. So
What time is that?
It's from 12 to 1.
This is on coming Saturday, is it?
Yeah, it's coming Saturday.
Okay. So, I will do one thing. I'll just send out, send out a poll to check when everybody is going to be most likely. Is that fine? And, if a small number of people miss out, there will always be recorded videos for you to catch up.
So I think next Wednesday is a holiday, so we can, I don't know if we can still have class on that day.
That's also a possibility if everybody is okay with it. If there are no other classes that day, we can have a longer class on next Wednesday also, right?
Yeah, that was what I thought.
Yeah. But again, it depends on UG students, really. If they have lots of classes, because they are the ones who are probably taking some 6-7 courses, it's hardest for them to find a slot that works. In fact, that might be the easiest solution, actually. Next Wednesday might be the easiest solution. Okay. So, maybe I'll get back to over, Canvas. Okay. So let's now try to analyze this and finish the analysis. So how do you go about mathematically analyzing this? Okay, the first thing is, let's go back to the equation and look at the equilibrium. So you will see that there is a factor y here, and there is a factor y here, which we can take out as a common factor. Is that right? And therefore, that also immediately gives us the equilibrium. And one equilibrium, therefore, will be, which is always true, is y star is 0, which is an extinction equilibrium. Okay. Now, what about now we can take y out of our equation. Okay, now we are left with 1 minus y by k and h divided by 1 plus y. Okay. So we will find other equilibrium. We may have one more or two more equilibrium, and those we need to solve the following equation. Is that fine? Okay, so we need to solve this equation. Again, think graphically. Let us think about this graphically. What does this mean? It is basically the intersection of two curves, right? The first curve is the left-hand side, which is starts at 1 and hits k. And the right-hand curve is h divided by 1 plus y. When y is equal to 0, what is this? This is basically h. Is that right? And then it decays to 0. Now you can already see there are, depending on the value of h, the intersection can be either, the h, if h is, let's say, less than 1, we have somewhere here. And then it goes off like this, giving rise to an intersection point here. Okay, on the other hand, if h is somewhere here, intermediate value, what can happen? It can do some, so sorry, it's a very bad drawing. Horrendous drawing. Okay, please excuse me with that. This is what can happen. Is that right? Okay, let me not maybe do circles at all here. And when it is really, really large, You have something like this. No intersections at all. That means no other equilibrium. Is that correct? H large. This is H small. Okay. So these are the three possibilities. And it is really in this case that you have again two additional equilibrium. Okay. So now let us try to do the following. Now we have an intuitive picture, right? When we also are getting some quantitative ideas here. When H is less than 1, what happens? When H is less than 1, you have only one other equilibrium. So let us now also sort of in another page, somewhere down below, start plotting the bifurcation diagram.
Sir, before we move on, there is a case where the h by 1 plus y graph is just tangent to the straight line, right?
Exactly. I'll come to that. It's a very good point. I'm going to come to it. Okay. Okay. So for h very low, you basically have this equilibrium, right? And then you remember that we always have one equilibrium. What is that? That is zero equilibrium. Okay. We are always a zero equilibrium. The question is, we don't know stability. Can you make some inferences about stability from this graph? We have already done that here, by the way, right? You know, for h is small, which is stable, zero is stable or unstable. For h small, zero is unstable. We know beyond some h, zero becomes stable, right? Up to some h, basically zero is unstable, meaning there will be some value of h here, after which h is stable. What is this value? Do you get a hint from this graph? What is the value h going to be?
1.
Right, so that's correct. Okay, so when h is actually less than 1, 0 will be unstable, and when h is beyond 1, 0 becomes stable. Does it make sense? Okay. Okay, now we have found out at least what happens to this graph. Let us again go back here. For h small value, we have this equilibrium. This will be a stable equilibrium, unstable equilibrium. This will be stable, right? Because that's what we found here. This equilibrium is stable as this equilibrium here for small h. Okay, this is a large population size equilibrium, and that is a stable equilibrium, and 0 is the unstable equilibrium. So we can actually also start thinking how this will look like. So k is the other equilibrium here, and what we have is, this is slowly reducing, and this is actually stable. It continues up to some time. Here is the thing. When h is very, very large, does this equilibrium exist? It doesn't exist, right? Because there is no intersection at all. So this equilibrium after a value of h basically just does not exist at all. This large equilibrium value does not exist, which means that when harvesting rates are very, very high, there is only one equilibrium, which is, extinction equilibrium. Okay. Now let's go back to this graph again. There is this scenario of two equilibrium in between, right? And just, imagine I plot for an intermediate value of h, something like this. You can observe a pattern here. The distance between these two equilibrium keeps reducing, and there will be some value of h where what you will find is a tangent here. So, this is a small, bigger value of h, even bigger. So as you go towards larger values of h, the distance between these two equilibrium, that keeps reducing. Okay. So now if I want to plot this equilibrium, which is actually unstable, as we have already figured out, this is how it will look like. Okay. So there are two equilibrium that are actually getting closer as we increase h. Okay. And if you sort of, work carefully, what you will find is something like this. So if you work hard to find every equilibrium and plot that together, this is what you will find. So there is basically a range of values of h. Let's call this hc. Okay. So between h0 and 1, we have a large population that is stable. Between h1 and hc, you have two stable equilibria. One large population size, another one is extinction. And beyond H greater than HC, you have only extinction equilibrium. Does it make sense? Or is it too hard to visualize this? So you'll have to work on your own to really make sense of this. And if this is true, there's another very interesting implication. What is that? There's something very interesting you're noting here. To sort of make the contrast, let me also plot what we found for the other model. We found a bifurcation diagram like this for the other model. The model we discussed last Wednesday. So what is the difference between these two? This is for the type 1 Hollings.
The current one have like abrupt change.
This is type 2. Okay, so this is, there is the population density decays gradually with the harvesting rates. Whereas in this case, if harvesting rate was to increase, the initial stages, the population will decay slowly and gradually, but there is a threshold value of harvesting at which what happens? The population will suddenly collapse. Does it make sense? Okay. And mathematically, these type of, so bifurcation, remember the word bifurcation? Bifurcation are points where the stability structure changes. This is the bifurcation point. This is another bifurcation point. This is another bifurcation point. So in this bifurcation, what happens? The stability of this equilibrium, zero equilibrium, changes from unstable to stable. Okay, and it happens in a gradual way. This is called transcritical bifurcation or a continuous bifurcation. Okay, whereas here this is called there are many names for this bifurcation. There's another name for this called fold bifurcation. Fold because there's a stable equilibrium of folding. It appears like folding structure. Okay, so you have fold bifurcation, subtle bifurcation. Okay, so any questions on this? Okay, so for those who can stay, I want to complete one more thing because we're really short on time. Okay, what I will do is I will now sort of do this bit more mathematically. Okay, so we have found this now, right? We have found this structure. And let us say we want to find what is this HC. What is the value of HC? What is the value of HC? How do we find that? So the HC basically corresponds to this curve where it becomes a tangent. Okay, HC basically corresponds to the scenario when the straight line, sorry, this is a straight line and basically both this curve are tangentially meeting. Okay, in the fact that they're actually meeting, because they are meeting, this must be true. Because they are tangentially meeting, one more condition must be true, which is that the slope of the two curves at this point must be also same. So what is the slope of this curve? If I were to now equate the slope, what I find is the left hand side will be 1 minus k, the right hand side will be minus of 1 plus y whole square. Okay, so h therefore is equal to k divided by, h is basically 1 plus y whole square, hc is basically 1 plus y whole square by k. But we don't know what is k yet. We don't know what is y. Okay, so one way to sort of find that out is what is the value of y at this, when they're becoming tangent. For that, we can actually solve this equation now. So how can we do that? So now we just look what we have. Any suggestions how to solve this equation?
Sir, can we convert
Both
that into
sides-
quadratic and then
can,
find the condition where we have equal roots?
We have equal. That's a good way. That's a good way. Okay, so we basically can take this and multiply these two equations. I thought there was maybe an easier way. Maybe there is.
The discriminant should be 0 for that quadratic.
Yeah. So why don't we? I think we can just do that. 1 plus y. So we are now solving this. 1 plus y into 1 minus y by k is equal to h. Okay. Yeah. Okay. I was just thinking hc is equal to this, which is also equal to. I think there may be a simpler way. If I set h is equal to 1 plus y into this is also equal to 1 plus y into 1 minus y by k, right? I can now set these two equal and I will get 1 plus y by k is equal to 1 minus y by k. Is that right? Huh? I think that might be an easier way. Okay, so now we have, oh, no, I think that leads to a problem. No, 1 plus y whole square, sorry. Maybe that doesn't help particularly, right? No, I thought it was, oh, no, that's actually, sorry, this is okay, yeah. You all of you understand how I got this? I don't know if you understood how I got this part.
By
Maybe I'll just
cancelling 1 plus y.
I mean, I'll just do this, carefully. Okay. So now basically from this equation, we got this. From this equation, I can take 1 plus y to the other side and basically say that hc is also equal to 1 plus y into 1 minus y by k. Is that right? So hc is equal to both of the expression. So basically I can equate the right hand side of this to the right hand side of this. That's how I got that. Okay. 1 plus y whole square by k is equal to 1 plus y into 1 minus y by k. Now this goes, so therefore 1 by k plus y by k is equal to 1 minus y by k. So y by k I'm going to take on the same side because eventually I want to solve for y, right? So I will take this on the other side. So 2y by k is equal to 1 minus 1 by k. This implies that basically y is equal to k by 2 into 1 minus 1 by k. Is that right? Is that right? And then I can substitute. So basically y is now known entirely in terms of k's. So I can substitute that in this expression or either of the expressions and I should be able to find a simpler solution for what exactly is the condition for hc. Okay. So that's one way to find the critical value of h. And you will also get a condition when that is actually true. Okay, so you will note one thing here very quickly. Y is equal to this, but we've always wanted y to be greater than 0, right? This implies that 1 minus 1 by k has to be greater than 0. So this implies that k has to be greater than 1. So if basically k is less than 1, you will not find this bistability. So this is true. This entire, this entire graph is true only if k is greater than 1. If k is less than 1, what do you find? What you will find is that you will again find a graph like this, even for this model. Okay, that is something I will leave it for you to sort of explore on your own. Okay, so we'll stop here today, and then we will meet again on Friday.
Sir, one small question. Can you go to the next slide?
This is the next slide. I mean the previous one.
Is there a reason why you written y equals k by 2 into 1 minus k as opposed to k minus 1 by 2 directly?
Say that again.
You can just multiply k inside and write y as k minus 1 by 2, right?
This entire expression, is it?
Yeah. Is there a reason why you've written it this way instead of
No, there is. I mean, I just haven't simplified.
Okay.
You're right. I can do that. Basically, k minus 1 by 2.
Yeah, then
That's
the
what you
condition
get?
becomes clearer, k greater than
Yeah,
1.
yeah, and in fact, it actually helps. So you remember, if you go back here, what is this? This is 1 plus y whole square, right? What is 1 plus y? 1 plus y therefore becomes k plus 1 by 2 whole square. Is that right? From this, 1 plus y becomes k plus 1 by 2. And now I can plug that in this previous equation. Okay. And what do we get? We have get k plus 1 whole square divided by 4k. So HC now is nicely expressed entirely in terms of k. Okay. Is that clear? So I don't even have to depend on, yeah, your suggestion helped me write down the final form of HC. Any other questions?
One question. I didn't understand the slope. How did we get that? I missed. I didn't. That wasn't clear to me.
This equation?
This equation, yeah.
So okay, basically to solve the, so this part is now very clear, right? This is also very clear, right?
Yeah.
This is the point of intersections.
Right.
So what I'm now trying to find is, what is the value of this HC in this graph where the two, you have only one equilibrium. And that happens when this blue curve and the black curve meet at the same point, right?
Right.
Now, if you go back to this graph, which is very, very ugly, I haven't written it well. Maybe I can write that again.
No, it's a tangent, right?
Exactly. Basically, when the right hand side and this function and this function, they meet as a tangent.
Right.
That's when basically corresponds to the case that both the two equilibrium have merged now. Okay, and beyond that value of h, there are no more equilibrium, right?
Yeah.
And therefore now what does it mean to say that the two graphs are meeting as a tangent? At the point of intersection, their slopes are equal. Right? That's what I have done by this equation. So this is the equation for the this is the equation that tells you where they meet. When they meet, their slopes must also be equal. So therefore, take the slope on both the sides. So the left-hand side slope is just first term is 0, second term is just a constant, right? Minus 1 over k. The right-hand side, the slope of this equation is h divided by 1 plus 5 square with a minus sign.
Okay, got it. Right.
So not only equating the equilibrium values, but also slope at the equilibrium.
Right. And so the other question I had was, what is K0? Like
K0 was the carrying capacity of the original system. Right. So if you go back to the equation,
so we have defined K as K0.
This is the K0 is the carrying capacity of the the system if there was no harvesting.
Oh, okay.
Right.
So carrying capacity changes with harvesting, or what? Or...
No, it doesn't change. We have just rescaled everything. See, remember earlier, carrying capacity was when we were writing the equation in terms of capital N.
Yeah.
Carrying capacity becomes, small, the K where is K0 by N0.
Yeah, so we have scaled our new carrying capacity with the population size.
N0. Half saturation constant. But remember that even the population measurement has been scaled by the same thing. See, now Y is also measured in the units of N0. K is also measured in the units of N0. So it doesn't really matter. So both are measured in the, so it's like, moving from centimeters to meters. Initially I was measuring both in centimeters. Now I'm measuring both in meters. Or, if you were to give an analogy in terms of length, it doesn't change anything though.
I have a follow-up question here. As you shared earlier in the class, that if we have three such measures of population, so then we can reduce. Like if you have three constants that say here, if you have carrying capacity and not, and we have another one also.
Okay.
So we can reduce only by one.
Yes.
So like the concept that you shared, it's just a measurement units. So
exactly, it's like changing the measurement unit. Exactly.
So we can scale it. So why not, if we have 3, so we can scale it by the same quantity and get a single one? So why only?
How can you get? It's not clear to me. So let's say I have 3 population sizes, right?
Okay.
Okay. One has a value of 50, other has a value of 150, other has 500. Okay. I can say 50 is the basic unit, and in terms of it, I have now 3 and 10.
Okay.
I need that. No, I can't make it any further. I can't reduce it any further. I still need those 3 and 10 to distinguish the two. All the 3, right? 1,
Yes.
3, and 10 becomes now that I can't reduce it any further, right?
Yes. Okay, fine.
A very general question.
Yeah.
So this model, like ecologists and policy people, like people who decide fisheries and stuff, do they use these kind of models?
So why don't you? That's a great question. Why don't you read the papers I have shared already? It's there are 2 papers I have shared that sort of discusses the implications of these models and how they have been applied. So there's, I think, one paper, especially there's a paper by Martin Scheffer and others in 2001, which sort of really puts them in an applied context. There is, of course, a 1977 Robert Mays paper that also does the same thing, but it is still, the mathematics is still the focus there. Okay, but in the context of the 2001 paper is a lot more applied in that sense. Okay.
Yeah, I'll take a look. Thanks.
Okay. Okay. If there are no more questions, we'll meet on Friday. See you everyone.
Thank you.
Bye. Bye.
Thank you.